Possiate amplificare, sì.
Da.
Danno poi da c'è che entrata.
Europe recovers from World War II. Many eminent scientists have left for the United States. European research is no longer world class. To reconstruct European science, the visionary French physicist and Nobel Prize winner Louis de Broglie proposes the creation of a European laboratory that would be both a centre of excellence in physics and a motor for peace. His idea is taken up by American Nobel Prize winner Isidore Rabi, who together with Pierre Auger and Eduardo Amaldi convinced UNESCO to adopt this process. 18 months later, 12 European nations formally agreed to create the Conseil Européen pour la Recherche Nucléaire. The acronym Cern is born. Important decisions are taken in the first sessions of the new council. Geneva is chosen as the seat because of its central location in Europe and its international tradition. Two accelerators are put forward, the Synchrocyclotron and a much larger machine, the proton synchrotron. A new convention defines Cern's goals, stating that its research will have no concern with military requirements and that all its results should be made public. The Cern Convention is signed by 12 nations. Among the signatories are eminent physicists such as Werner Heisenberg. Cern comes into existence. 1954. On a site in Meyrin, a small village near Geneva, work for the new laboratory begins. Within a year, the farmland is transformed into a large complex of workshops, offices and buildings to house the new accelerators. The 5-meter thick walls of the Synchrocyclotron building soon emerge, while the different parts of the new accelerators are manufactured in several European countries. The Synchrocyclotron's magnet coils require particular care to pass through some of the Swiss villages on their way to Meyrin. As components arrive, they are assembled with great precision. Everything starts to take shape. The Synchrocyclotron emerges, piece by piece. Some 54 elements are put together for the magnet frame. A total of 2,500 tons of steel. Next, the two 7.2 meter diameter magnet coils are installed. With a current of 1,800 amps, they generate a magnetic field of 2 Tesla. The rectangular vacuum chamber is fixed inside the magnet. A system of large vacuum pumps is installed to evacuate the 25 cubic meter chamber so the protons can circulate unimpeded. This is followed by the installation of 2 D-shaped electrodes inside the vacuum chamber. Together with these electrodes, the radio frequency generator creates the electric fields. That accelerate protons from a source inserted in the center of the vacuum chamber. In summer 1957, the Synchrocyclotron is ready, and Cern's first accelerator comes to life. The purpose of the Synchrocyclotron is to produce and study new particles. Before accelerators were available, such particles could only be observed in cosmic ray experiments. The new machine accelerates protons to 80% the speed of light, producing millions of new particles when those protons collide with the target, giving scientists the opportunity to make systematic measurements. Operation of the SC requires a sequence of actions. Massive pumps extract the air from the vacuum chamber so that protons do not collide with gas molecules during their acceleration. In the proton source, hydrogen gas is ionized and a cloud of protons is injected into the middle of the synchrocyclotron. The accelerator makes use of magnetic and electric fields. The magnetic field is produced by a current of 1,800 amps flowing through the coils of the huge magnet. Two D-shaped electrodes with opposite polarity are fixed inside the vacuum chamber in the middle of the magnet. Protons have a positive charge and are drawn towards the negative electrode as they traverse the gap between the electrodes. The magnetic field forces them to follow a circular trajectory, and they return to the gap after 1/2 turn. Meanwhile, the radio frequency generator reverses the polarity between the two electrodes. The protons are now attracted to the opposite electrode and gain more energy. This process is repeated over and over again. Every time the protons make a 1/2 turn, they are whipped around faster and the radius of their path increases. After more than 100,000 turns, they have reached an energy of 600 million electron volts and move at 80% of the speed of light. They are now close to hitting the target, and the first experiment can begin. In 1957, young scientists from all over Europe arrive. Among them are Maria and Giuseppe Finicaro. Giuseppe wants to study a short-lived particle called the pion. In 1957, there was a mystery surrounding the pion. Theory predicted that a direct decay into an electron and a neutrino should happen, but this had never been observed.
Phenomenology of this process. Only later on in 1957, when with the theory of V-minus theory, the problem was some kind of solid theoretical basis. So at the moment, the absence of the pi decay was very critical. It was essentially a block for the physics to go through. It was felt like a block. And there was at that time, in January 1958, that I thought that was the right moment to do this type of experiment.
Giuseppe and his team set up a clever experiment. The pions are stocked in an apparatus designed to study their subsequent decay. In 1958, only a few hours after they start the experiment, the first pictures show clear evidence for this rare decay.
I can imagine. I was really excited, very surprised. I can't describe it. I mean, it was something essential because something I want to see, something from this time. It's a thing.
This first important discovery spread Cern's name around the world. Over the following years, scientists at the SC continued to make many important measurements on particles, atoms, and nuclei. 1967, a new idea takes shape called ISOLD, an isotope separation device. Protons from the synchrocyclotron collide with target nuclei that are split into short-lived fragments, which are then rapidly scrutinized in experiments. The study of such short-lived nuclei with too many or too few neutrons helps to understand how heavy elements are produced in exploding stars. The synchrocyclotron accelerates its last beams in December 1990. After 33 years of an exceptionally long and successful career, the SC is retired.
Well, we felt that the Synchrocyclotron had worked very well and much more long and even was much more hot than anybody ever expected. Because he renewed in the field of physics, explored in the 33 years. He passed, explored many different fields and been very useful.
Following the Synchrocyclotron's construction, Cern built bigger and bigger accelerators. The proton synchrotron, the intersecting storage rings, the superproton synchrotron, the large electron-positron collider, and the Large Hadron Collider. Many important achievements were made, some of them being rewarded with the Nobel Prize. The drift chamber, which revolutionized particle detection. The cooling of particle beams. The discovery of the carriers of the weak interaction. And the Higgs boson, which proves the existence of the Brout-Englert Higgs field. In 1989, Tim Berners-Lee, while working at Cern, created the World Wide Web, which has since changed our world forever. The Large Hadron Collider will continue to run at higher energy and higher intensity, with more than 11,000 scientists from over 100 nationalities, hoping for new insights into the secrets of the universe.
I think that the curiosity and the need to do research is inside is a part of our humanity. So there will be always a Cern. So there will be Cern in the future.
What started once as a vision for European science has grown into a unique model for global scientific and technological collaboration. Cern demonstrates how science can unite nations and contribute to a better world.